Hi there, guys. Well, we've done 1I, which was the binomial theorem or the binomial expansion. So expansions of two things inside the brackets, like a plus b to the power of n, where n was a natural number, a positive natural number. So we're talking about n is 1, 2, 3, 4, and so on. Okay, so now when n, or our index number, is either negative or rational, we have two extensions to the binomial theorem. Now, the good news is, in the formula booklet, we have the binomial expansion, so the binomial theorem, expansion of these brackets. That's given to us, but to be honest, you'll get so much practice with that, that's pretty obvious. And each of those terms will become pretty obvious. In particular, in this formula, let's just steal this. I was going to talk about that, but this, in particular, in this formula, this is the key term. So this is the general term anywhere in the middle, and all of the other terms satisfy the same conditions as this middle term here. So really, you only need to remember this. You don't need to remember anything because it's in the formula booklet. Okay. However, these two formulas are not in the formula booklet. Oh dear. So they're pretty niche formulas, and it's kind of annoying that they're not given to you because you only use them occasionally. So the formula booklet is useful when you've got things which you don't want to remember because you rarely use them. You know, maybe that you proved them before, but so it's frustrating. You're going to have to remember them. So let me talk through them, and hopefully after talking through them, there's some kind of tips as to how to remember them, how they're set up. And let's just get rid of me. No, don't know what that's about. Okay, right. So let's come up with the easier of the two here. Let's come up with this one. So this is talking about rational powers, so rational index numbers, and they've used an A here or an alpha, just to differentiate it from using the N. So just so that when you're thinking about this, you can remember it's a different formula because they're not using N. Now this one is pretty straightforward, and there's not a proof for this. I think they ask you to check it later on, but there's not a proof for it. But each of these terms here, the 1, the alpha, this thing here, and this thing here, that just comes from your NCR. But in this case, because n is alpha, we've got alpha CR. I'm going to say A, okay? It's just easier to write and say. So ACR. So for example, if we try AC3, that's the same as A factorial divided by A minus 3 factorial times by 3 factorial. Well, you know that A factorial also contains A minus 3 factorial. In fact, it's A times A minus 1 times A minus 2 times this thing here. But then it will cancel with this thing here, the A minus 3 all factorial, and then you'll just have the 3 factorial on the bottom. So this is just the normal expansion of NCR. They've just simplified it in the formula for you. So this is the same as your normal binomial expansion. The only difference here is that it carries on forever. Now they come up with a general term here, and to be honest, I wouldn't remember that general term. I mean, you could call this thing outside the front A choose R, and then x to the power of r. I mean, I guess you can remember that, and you can see that we're summing this from r is equal to 0 to infinity, essentially. So this is going on to infinity, and hopefully when you maybe substitute in a value of x, you'll find out that those terms become more insignificant. A bit like when we do 0.01 to the power of, I don't know, 5, it becomes extremely small and kind of insignificant to the rest of the expansion. Okay, we'll deal with that in some of the questions. Hopefully they'll turn up. Okay, so this one is not too difficult to remember. And I would just remember that you've got your ACR, your NCR essentially, and it's just increasing powers of x. So instead of starting with maybe x to the power of a, we're doing the x to the power of a at the other end, and we're starting with the 1, so we're going from 1 to the power of alpha, 1 to the power of alpha minus 1, and so on. But either way, this is going from a to x to the 0, x to the 1, x squared, and so on. Okay, hopefully you've got some way of remembering this now, but it's pretty much the same as the previous one, except for there's a dot, dot, dot. It carries on forever. Okay, and I mean, I guess that makes some sense, right? Because if you were saying a is 5, well, you're going to have 6 terms, and you know that the terms increase in terms of powers here, and they decrease in terms of powers for the other one. And when you have to the power of a rational number, when you decrease by 1 each time, you're not necessarily going to finish the sequence. So there's some sort of sense to this, even though that's not a proof. Okay, so there's that one going on a little bit here. Now the other one is less obvious. And in fact, let's just have a look at how they started this one off, because this is pretty interesting, in fact. So the way in which they started this off, and you can play around with this as well, is they said, well, okay, I don't know how to expand 1 minus x to the power of minus 1. Okay, and note instead here they've put a minus x here, not a plus x, and we'll talk about that a bit more in a bit. But they've realized that they've kind of figured this out, that if you start with this sequence here, they've sort of done it the wrong way around. You can see that this is the summation of an infinite series, and this is an infinite series which is geometric. So our common ratio in this case is x. We go from 1 to the next, timesing by x. And our first number is a. And as long as the condition is met that x is less than, the modulus of x is less than 1, so it's the same as the sum to infinity condition, then we can say that the summation of all of this is equal to this. Okay. So, and now this, forward again, now this thing here is the same as this thing here, 1 minus x to the minus 1. So they've done this through the geometric series, or the summation of a geometric sequence. Okay, so they've not done a normal expansion. There's no normal expansion which you can do in this case. Right, so if you've followed that, then for the next one, to get the next power up, they're going to times 2 of these things together. So they've said, okay, well, let's do this times this, and it gives us 1 minus x to the power of minus 2 there. Okay, and so now let's times those two brackets together. And when you do times those two brackets together, you will notice that you get 1 times everything in here, and then x times by everything in here. So it's going to push everything on by 1, and then x squared times by everything in here, so on. Okay, and so that's ultimately going to give us one way of getting a 1, 2 ways of getting an x, and so on in this sequence. So we're going to get 1, 2, 3, 4. Well, that's pretty nice. Now you're going to need to do that again to get 1 minus x to the power of minus 3. Okay, so that's going to build up your sequence. Now, that's not a proof, that's just showing how the sequence develops. And in the book, it's kind of interesting. They say Newton generalizes this result for negative and rational exponents of the binomial theorem as follows. Okay, well, they're talking about a bit of maths history there. You're not going to be tested on that, but this is the era of Newton and Gauss. I mean, there's some interesting stuff there. You might want to read up on Newton and Gauss. I was just checking through some stuff as well. Newton's slightly older than Gauss. Listen, that's extra. Let's not go into it right now. Okay, anyway, the formula which comes up from this binomial expansion. So the second one which you're going to need to remember for negative powers is this. Okay, now this is more complicated because you can see that the n's, these terms here are increasing this time. So this is much less obvious. Instead of saying previously we had the alpha and the alpha minus 1 divided by 2 factorial, the difference in this case is that we end up with alpha plus 1. Again, I'm offering no proof in this case. We're just talking about how to set this one up. So for negative powers, we're going to increase here. We're still going to have the same 1x, x squared, x cubed, and so on. But this is going to be, the terms that we get out here are not going to be your normal NCR. This is going to be increasing amounts of n inside those brackets. I guess that's kind of obvious from how you see that. Now, I would just remember these things here. Now, they talk about trying to set that up as a summation of terms using NCRs. And to be honest, I think I would just remember these things here. I would just remember that in one of these sequences, the n's increase, and in the other one, for rational numbers, the n's or the alphas decrease, as you would normally expect. Okay, so that's the main difference between these two things, and that's how I would remember it. Now, remember there's an extra condition on this because of the way we set up that first one, 1 over minus x, that's the sum to infinity of our geometric sequence. So because the sum to infinity only exists with r being in between minus 1 and 1, well, we've got the same issue here as well. So we need to use that. Okay, so that's our condition. By the way, that's going to make some sense later on, because if you remember from the previous exercise, when we had the expansion of 2.03 to the power of 5, to the power of 5, I think it was, we chose a number here to be, I think it was 3x there or 3y there. We chose that number to be 0.01. So as you do x to the power of higher powers, that's going to become increasingly insignificant. And we know that as well because of this condition. Our common ratio, if you like, or our x value has to be between minus 1 and 1. Okay, right, so that's chatting around it. Let's actually have a look at some of the questions. There was, just one final thing, okay? If you want to, you can remember these things like this. Zoom in a little bit and steal this. Okay, so for this one, the negative integer powers, they simplify it like this. And so they say, well, this is your NCR in the case, this is your NCR here. Okay, just messing up on this one there, so I'm just gonna have to do this again. Now, if I'm messing up on this, this is not a great way of remembering the formula. As I said, probably better to remember that n increases for negative numbers and it decreases, as you would expect in the formula in those brackets for your rational powers. Now, again, okay. So what I was just doing here was coming up with a term in the middle. So I was saying, well, maybe let's look at what happens when n is equal to 3 for this simplified, supposedly simplified version of doing this expansion here. So when we look at r, did I say n is equal to 3? R is equal to 3 is what I mean. So the third term here, you can see it goes up to infinity. So in this case, for the third term, we'd get n plus 3 minus 1, choose 3, and then x to the 3. That would be our term. So now we're going to need to figure out what this is, because that's our coefficient of x to the power of 3, and that's the difficult thing to remember. And so we'd have here n plus 3 minus 1. So in other words, n plus 2 factorial divided by, now what do you have underneath? You would have 3 factorial, that's the easy bit, but then this take away the 3. So with that take away the 3, this would cancel here, so you get the n minus 1 factorial. See why this is really messy. And now this definitely includes this. So we'd have n squared, n plus 1, n, and then we'd have n minus 1 factorial, which is going to cancel with this bit here. then divided by 3 factorial, and that's going to be your term in front. So this thing here for the third term is going to give us this, and then x cubed, and then x cubed on the end. So you can remember the whole formula like this if you want to. I just think that that's unnecessarily complicating things. In the book, they say show that. So this is investigation 20. They just say show that the generalized form for the negative integer powers given above can be written as this thing here. I've just shown it for one of the terms there. Again, the investigations are nice here. If you're not familiar with these formulas, the investigation helps you become familiar with the formulas. Okay, right. Oh, and one extra final thing. Okay, so one extra final thing is that it's not always written as x minus 1 to the minus n. That's the way in which the Oxford book is doing it. And I don't know how IB want you to do it, but often people will use this alternative version. Let's just snip this one here. This comes from Wolfram Alpha. So let's just snip this. And you can see that they've still got the 1 over 3 factorial here, 1 over 2 factorial, and so on. So this is the same formula here, except for you'll notice that you have minus, plus, minus, plus. You have these alternating minuses and plus to start off with as well. So the problem is when you have a plus 1 in the center, you get minuses in the formula, which is probably more difficult to remember than remembering that x minus 1 to the minus n just gives you this whole thing with pluses in between. So 1 plus nx plus n plus 1x squared over 2 factorial, and so on. So I think that this one is probably easier to remember. So I think the Oxford book has kind of done you a favor there, but you might have been questioning why it is that you're having a plus 1 in the center there. Now, you might also be questioning why we're not doing a plus b, but you can imagine it's going to get a lot more complicated when we're doing a plus b power of minus n. Okay, so in your questions, it might be that you have, say, for example, I don't know, you might have 1 plus 2x to the power of minus n. So you just realize that you need to substitute in 2x where you see your x. Yeah, I think that's enough in terms of explanations. So that's going on. Let's deal with the 2 questions. And here we go, example 52. So expand the following up to the term in x to the power of 3. So obviously we can just use our 1 plus 2x here, power of a half. So we can use our laws of indices there just to write this one down. Our condition is satisfied for us to be able to use the formula. So that's all that this is saying over to the side. And now we need to use the formula. So remember that the formula is, and I would probably write it down, 1 plus, let's use the ax plus a minus 1x over 2 or 2 factorial plus a minus 1, a minus 2 x squared. No, x cubed. You can see where I've gone wrong there. It's an x squared. And there's a 3 factorial, and it carries on forever. But it says we only need to go up to x to the power of 3. Now, clearly, all you need to do here is substitute in numbers. So you can substitute in your a is equal to a half. Okay, so you can put that in here. That's clear what that's going to be. And this might be on a non-calculated paper, so you're going to need to be good with working with your fractions. So perhaps let's take, for example, this one. We've got a half minus a half times minus 3 over 2 over 3 factorial. It is important that you get practice with this, writing it out, not just on your calculator, of course. And you can see that this one, this coefficient is going to equal to, what's that? 3/8 divided by 3 times 2 times 1. Let's cancel a 3. And then we've got 8 1/8 divided by 2. So we're getting 1/16 in that case. Okay, so you're going to need to be good at your fractions work and your number work in this case, and working with fractions inside fractions as well. So it's worth doing these longhand. Okay, so there's that one. Obviously, you're going to do your substitutions in, and you can do a substitution in for this one as well. Let's just check the book, what answer they come up with. And they come up with a different answer to me. Oh, they come up to a different answer to me because I've not finished my question. Do you see how I've not finished the question? This is why I shouldn't be skipping steps. I haven't actually substituted in here what I need to substitute in for x. So in this case, x becomes 2x. So we're not finished when we've got to 1/16 because we also need to do 2x cubed, which will give us 8x cubed. That's why it will cancel 8 and times the 16th gives us the half there. Okay, now you can do that yourself, of course, but essentially, once you've identified the correct formula, so once you've identified this, and once you've identified that a is equal to a half, and that x becomes 2x in our formula, then it's a matter of substituting in and just grinding out the number work. Okay, so let's get rid of all of this and let's look at part B. So part B is now saying 2, and let's again use our laws of indices here. 1 minus 3x power of minus 1. So again, we're going to need to set up our form here. So remember, we've got 1 minus x to the power of minus n. And I would write down the original formula that you remember. I wouldn't skip that step. So we've got 1 minus x to the power of minus n gives us the 1 plus nx plus n plus 1 2 factorial, which is just 2, of course. And we've got n plus 1, n plus 2, x cubed over 3 factorial. Practice writing that down, practice hiding that up and writing that down. We don't need to go further than that. Obviously, that is dot, dot, but we can stop there at x cubed in this question. Okay, the condition for this working is also satisfied. And so that's all that this is saying. And so now we need to put in our numbers in here. So we're going to need to say that x becomes minus 3x in each of these cases. So here, 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 and here. We're going to substitute that in using brackets. And n in these cases, n is going to be here. So n is our n becomes, or actually we can just say it's equal to minus 1. And then when we've got all of our terms, we then need to remember that the whole of this thing is going to be times by 2 as well. So once you've substituted these things into here, you'll then need to say, well, okay, that's going to be giving you 1 minus 3x minus 1. But then in order to get the answer to 2 lots of that, you will need to double everything. Okay, I'm not going to do that now. It's going to take a lot of time working that one out, and it's pretty dull, to be honest. So obviously make sure that you're getting practice doing that. You can see that they've done exactly the same here as well. Okay, so example 53. Let's take this. Example 53. So use the binomial expansion to show this statement here. And they say here is approximately equals to, which is kind of interesting because they haven't asked us to find out any further terms. So x cubed, x to the power 4, and so on are going to become more and more insignificant, seeing as the modulus of x is less than 1. So they're going to be smaller and smaller answers when we substitute in a number which is less than 1. So the first terms are the most significant terms. So the terms afterwards, they're saying here that we're not interested in them. They're saying that because they're saying just equals to up to x to the power of 2. We're not interested beyond that. Okay, so we're going to need to try and figure out how to do this, but we can see that in fact we could split this up. So again, just laws of indices being used here. So we could split this up. We're going to need to do a little work here and say, well, that's the square root of both the top and the bottom. That's this to the power of a half divided by 1 minus x to the power of a half. But then, of course, that's the same as doing 1 plus x to the power of a half multiplied by 1 minus x to the power of minus a half. Okay, if you notice that I'm getting a little tetchy here, it's because I've messed up here another couple of times, and so I've had to just go back. And it just goes to show you that it's, although this is basically just substitutions, you just really need to be very careful in your lines of algebra and to be really thinking at each stage, what is it that I'm substituting in, and give yourself enough lines to keep simplifying throughout those lines. Okay, so here we go. So this was where we got to before. This was 1 plus x to the power of a half and 1 minus x to the power of minus a half. Now, notice that we have two rational numbers here. And what I forgot to mention from before is that, there we go, just go up. The binomial expansion extension started with negative integers to the power of minus n there, and then it went on to rational numbers. Now, rational numbers can be positive or negative. So this includes rational negative numbers when you get to this second binomial expansion here. Okay, so you might be questioning in this case, you might be saying to yourself, well, what do I use, the negative version or the rational number version? Well, this is a rational number. The negative version only talked about negative integers. It didn't talk about rational numbers. So you need to use the rational rational index binomial expansion twice here. It's that version that you need to use. Now, this is that version, which is what I've written down here. And now I've done my substitutions, and this is where I was messing up a little bit. The first one is absolutely straightforward. You can see that you've got your normal, this is the same as this, just with a or alpha replaced by a half, and so that's exactly what I've done here. And I've just replaced alpha by a half there, so that's fine. But in the next one, you need to notice that there's two things which you're substituting in with negatives, and that's where I was slightly messing up. And you know, negatives are such a common source of mistakes throughout your working out. It can lead to a lot of lost accuracy marks in tests. So we've got here a, and we've got a and a minus 1 here as well. Okay, and then we've got to remember that this is for plus x. So really we have a plus minus x. So we need to substitute minus x into each of the x values which we have here. So we're substituting in minus x there and minus x there. Obviously, it doesn't make any difference here, but it does make a difference to this middle term here. Okay, now you can simplify this. So this is basically a little bit of working out a side. This is just our formula. And this thing is still equal to this thing here. And we should connect things up for the examiner to show that our lines show our logical steps. Okay, so now we need to multiply these two things out, but some terms aren't going to be relevant. So simplify obviously first, and then you're going to need to multiply them out. Some terms like x squared times by x squared is not going to be important because we get x squared as our highest power and not x to the power 4. So I'm not going to simplify that just for the moment. Knowing how things are at the moment, I'm likely to make a mistake on that. So we're going to look at the book for that one in a second. But let me just get rid of this and just explain a little bit of the next theory, if you like. And that's if we do x to the 0, x to the 1, x squared multiplied by a set of brackets with x to the 0, which obviously is a constant term, x to the 1, and then x squared, then you're going to get out x to the 0 there, x to the 1 there, and then x squared here. So 1 times x to the 1 is x squared. The 1's in there, just completeness. And then anything after that is going to be x cubed or x to the power 4. X cubes are going to be there, x to the power 4 is going to be there. So we don't need to bother doing these terms here. So when we do our 1, 2, 3 times by 1, 2, 3 terms, we should end up with these 6 terms here, and they're the ones which we're going to be adding together. But when you do that, you go 1, 2, 3, 4, 5, 6, and you do plus dot dot dot. Okay, because the other things we don't care about. Okay, well, the book does that slightly differently, and actually I quite like the way the book does it. So when the book does this one, so by the way, there's the answers, 1 plus x over 2 minus x squared over 8 is in one bracket, and 1 plus x over 2 plus 3 over 8 x squared for the next one. Okay, and they put dot 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 there saying it continues forever, but we don't care about those terms. So just to look at how the book does this, because this is a pretty nice layout as well. So they've said, well, look, let's do 1 times these terms gives us these terms. Let's do this times these terms. Now you're going to not worry about that last one because that's going to give you x cubed. So you'll only need to do the yellow one times the 2 at the front. And so that gives you those answers. And the blue ones, which I'm going to make blue now, so it's this times the first term. And we don't need to worry about doing the terms after that because it's going to give you x cubed again. But we're just going to get this here. Now you can add, what's quite nice about this, you can add this, this, and this. You can add down the columns. So you can see a half of x plus a half of x gives you a whole x. Okay, and then you can add your eighths together here as well. You change that into eighths. Okay, so this could be a non-calculated question as well, and there's just a lot of algebraic work which you need to become fast at. So you need a lot of practice at this. Okay, right. Well, I can finally finish talking here. A little TOK bit in the book, a little extra. Okay, so 1J has 7 questions, and you can see that I've been making mistakes on this. And to get to the point where you're not making mistakes, you just need a lot of practice. And to be honest, I haven't been practicing these a lot lately myself. So, you know, practice does make perfect in this case. Okay, there are none of those types of questions here, just as a little extension. Let's just take a little bit here. There's often a type of question, and I can't see that here. No, I can't see that here. Where they'll say something like, can you evaluate, let's say, I don't know, 1, I don't know, they say 1 plus 0, 1 plus 0, 1.03 to the power of, I don't know, let's say minus a half. Now, in that case, you could work out your expansion to 1 plus x to the power of alpha. So we've got 1 plus something here. And then once you've come up with your simplified term here, you can then substitute in x is equal to 0.03, for example. Or it may be, even nicer actually, I think, if we did this, then we can substitute in x is equal to 0.01. Now, there's a question like this before. So, hang on, we can take the minus a half. So we can do this expansion here in order to help us with this calculation here. Because obviously, how would you do this without a calculator? Well, the answer is you do it through a binomial expansion. Now, when you start substituting in, again, 0.01 into terms like x to the power of 5, this becomes really negligible, really extremely small. So if we're only looking to something for an answer to something to say, for example, three or 4 significant figures, then we're not going to need to go up to too many terms in this series here. Okay, so that's a common type of extension to these questions, and I can't see that here. So obviously this question would be set to say, can you expand this up to, say, x to the power of 5, and then can you come up with an approximation to this answer here by using that expansion? Okay, another possible question here, so just for some of that, think back in my memory to exam questions, is sometimes instead of putting a 1 at the front, they might put, say, for example, a 2 at the front. So you might get 2 plus x to the power of, And let's put minus a half there again. Now, when you have a look at this one, you think, well, that's not in the form of 1 plus x. So what you'll need to do is put it in the form of 1 plus x by putting 1 plus, by factorizing this to start off with, by taking out a 2. So we'll be left with 1 plus x over 2 there. And then that's to the power of a half. And then we can use our laws of indices by saying a b to the power of n is the same as a to the n b to the n. So we can split this up to say 2 to the power of minus a half times by 1 plus x over 2 to the power of minus a half. We really need those extra brackets there. And now we've got this in the form which we can deal with because our formula, remember, has 1 plus x to the power of alpha. Okay, so we need to make sure that we're creating a 1 plus something. So this is kind of tricky to start off with, and you might be questioning, what do you do with the 2? So what do you do with the 2? Well, you factorize it out, and then you actually use your laws of indices. And now you can say this bit at the front is actually 1 over the square root of 2. And then you've got this expansion here, which you can then work out using the binomial expansion. I've talked myself into the ground here, so I'm going to stop. And thank you for listening. That is actually the end of this chapter. You've got the chapter summary in this excellent Oxford HLAA book. And so you've got the chapter summary here, a ton of stuff that we've covered, and a little bit of an extra. They're always chucking in extra things here, little investigation. Maybe some of these investigations could turn into IAs, so your coursework, your internal assessments. And then you have your chapter review, and the chapter review is fantastic because it's now really testing all of these ideas separately. Now, if you don't have time to do this during the main part of the course, you should be going through this as a review before your tests. And again, they're all fantastic exam style questions there, but then they become more exam style when they actually give you the amount of marks available for the questions and the difficulty for these things after question 17 up to question 25. Guys, you've got your work cut out here. You've got many, many, many hours of work here. We know this course is hard. Get as much practice as you possibly can. Okay, thanks for listening, and I'll see you later for the next chapter.